Swayam Prabha. Digital India. Educated India.
Modeled and how they are analyzed. Okay. This is a typical, you may say, diagram of a helicopter rotor blade. So, this is a rotor hub, of course, you have attachment, then outboard segment, then you have pitch bearing, then this is the inboard segment, then this is the tip. You can have different tip shapes. Even now it is not fully clear which tip shape is the best for what. It is all, each company has their own, evolved with a particular tip shape and they use that particular shape. Okay. You will find variety of shapes, all right. And of course, you say this is the flap motion, this is a lead lag motion and this is a torsional motion. When I say torsion means it is the elastic torsion. Okay. Pitch angle you change at the root of the blade, but the blade also can twist elastically. Okay. That is equally important when you are analyzing the actual blade, because your angle of attack changes. Now, this is a large aspect ratio, in the sense usually it is about 20-25 feet. I just brought one, this is the actual cross section of a rotor blade. This is the cross section and you see the trailing edge is just a honeycomb, this is a metallic, of course there are composite blades. The trailing edge is honeycomb, it just gives only shape, okay. There is nothing else. All the load carrying part is done by only this section, the D section you can call it, and you will see the leading edge is a little thicker. So, this whole design is made such a way that the, I will show a typical section of a, this is the rotor blade cross, typical section, just similar to this. Okay. Only thing is each blade has its own section. This is the real life actual blade cross section. You always put a leading edge weight, that is to shift the center of mass to 25% card from aeroelastic considerations. Okay, we will learn that. I do not think in this course we will be able to learn. And then of course, your aerodynamic center is 25%, take it as 25% because subsonic. Then you also make sure that shear center is at 25%. That means the design of your cross section is very important, where you put that, this vertical member, this basically this portion. So, that this is your load carrying, you can see where the shear center will be, and that you try to keep it at 25%, but not all designs have to be like that. Here he has given some, okay. See, this is the spar and this is just honeycomb, or sometimes they fill up with foam, very light foam, that is just to give a shape, that is all. And main leading edge weight, this section, and this is the foam. Sometimes here there is foam, here in this case there is no foam, it is just a hollow. Okay. Now, if we try to write the, this beam is going to undergo, I will put it introduction just to say, when you want to study the blade dynamics, Okay. You need to have the structural model. Structural model means essentially the how the elastic properties vary along the blade. It is a beam type structure, because helicopter rotor blade always it is analyzed as a beam. Then of course, you have to have a inertia model, then the aerodynamic model. These three if you have, you can study structural dynamics and aeroelastic analysis of rotor blades. People have spent their entire research career only on this, just sometimes only modeling the structure. Okay. Now, the key difference between the conventional non-rotating beam and a rotating beam, if you consider, one is we introduce centrifugal and Coriolis effects. These are because of rotation, okay, and this you cannot neglect it. So, this is the difference between a beam which is not rotating, which you study in your aircraft structures 1, but here is a beam which is a rotating beam. So, you have a centrifugal and Coriolis, both will come because of the deformation. Then of course, you will have, I put nonlinear because it comes because of axial deformation. Okay. You have to take, because of the centrifugal force, you need to, how do you account for it? There is earlier days they were taking it in approximate manner, but if you systematically derive the equation, you will find it is a nonlinear equation. What type of nonlinearity is? Strain to displacement is nonlinear. Please note, strain to displacement, that is one nonlinearity which is called the geometric nonlinearity. Okay. Strain to displacement relation. Okay. Another one you can have stress strain relation. Okay. Okay. These are the two in any structural modeling, there is nothing more. All the problems of what type of material, that comes here, whether it is a composite, isotropic, anything, that is only in the strain displacement relation. But stress relation, strain displacement relation is purely kinematics, that is the deformation, how the strain at any point is, what is the value of the strain in terms of the deformation. Okay. And you can, this is what is the nonlinear expression. If you take only linear term, you will find that you will not be able to get the proper representation of the rotating beam. So, that is the key. You have to have the nonlinear relation. So, this particular type of nonlinearity you call it geometric nonlinear. Geometric nonlinearity. Whereas this is stress strain relation nonlinear means that is the material nonlinearity. So, you call this material nonlinearity. Okay. These are the basic things, but we do not go to material nonlinearity. The key is whenever you design a blade, you make sure that the strains are small, actually infinitesimal strain. Strain is small, but strain to displacement is not small, because the displacements are, they do not say large, they say moderate deformation. It is not a small deformation. That is why this relationship is nonlinear. Okay. and that is why I put geometric nonlinearities have to be considered if you want to have a proper treatment of this blade analysis. Now, just to give you a brief history, see isotropic blade, okay, real formulation started actually in 1950s. Hobolt and Brooks, that was the first paper he wrote on axial, flap bending, lag bending, torsion. But then that was the first paper. There were mistakes, okay, few mistakes. Subsequently, groups have started. Actually, the groups, you will be surprised, one group is actual turbine blade type of analysis. Another group is a rotor blade, okay, other two groups, because one group was at NASA Lewis Center, other was some universities. So, they started deriving the equations for a beam, please understand beam equations. So, it is all isotropic blade first they in 1980s, but then composites people started using. So, again after 1980 composite blade formulation, then what are the various things you have to consider? Is there anything extra? Suppose if you have a one general formulation which fits into everything, then it is beautiful. But unfortunately, when you are starting the development, always you make approximations because you need to get something. So, they used the cross sectional shear deformation was neglected here. Then they said we will add this. Then of course, warping, bending warping, various types of warping. Of course, torsion is warping for torsion is important, that has to be considered here. Then of course, people also develop large deflection, moderate deflection. Moderate means you make some approximation, okay. Because if you use this type of I am not writing any equation here, you will find the strain expression itself will be missing, strain to displacement. You will have lot of terms, okay. One is terms, another one is you have to now analyze what is the blade dynamics and then aeroelastic behavior, that is all, only these two. But to know whether your equations are correct or not, so there has to be some experimental study. So, one experiment, that is why I said sometimes one simple experiment will give a very thorough understanding on the status of your knowledge. So, this experiment, it is called the Princeton beam, because it was done at Princeton, okay. Very simple experiment. You can look at the web page, you will see. Experiment is you take a beam, it is not a twisted beam or anything like that, straight beam. So, we all know that beam means you take it like this, sorry, okay. Instead of taking it in this fashion, you slightly okay, rotate it, and then when you apply the load like this, it will take a load this way and this way, okay. The beam cross section, if it is flat, you apply the load, this is the beam bending. You want it to bend in both directions. So, instead of that, they just took the beam, kept it little inclined, apply the load, that means the tip load will give deflection in the blade coordinate, it will give in both. So, this experiment was conducted for slightly moderate deflection, large deflection you may call it. Then the data was given. Initially people could not get that experimental data. Then they went back, again looked at the whole equations, started re-deriving, and then finally they got the results. That means you now know, hey, I am able to solve a bending problem, very simple experiment. That was the time people, now equations are fairly well established. You know that what is the procedure to develop the equations and then get the equation of motion for a rotor blade, twisted beam, no problem. Only thing is that now of course there are assumptions made, the complexities come in the aerodynamics now. So now when you look at the actual, I have written here the modeling, you treat it as a beam model, nothing else. Okay. But then rotor configuration, if you look at it, you will have pre-cone, pre-droop, I will tell you what those things are. Then it can have pre-sweep, pre-twist, then torque offset, root offset. These are all geometrical quantities which will be there in an actual rotor blade. Now you need to take all this, and of course additional complexity is if the hub itself is moving. Okay, hub is fixed is one. Suppose hub moves, in addition the blade is moving, then the problem becomes more complex. In the earlier formulation, only they will take pre-cone, which we have used beta P, just very simple, but not all the other quantities will. Root offset, I will show you, we take that. Key things they will take, rest of them. But then when you want to take all of them, then the derivation becomes messier. But now it is, you can take all these quantities in your blade model. I will show you just a diagram, both very exaggerated view. This is an exaggerated view. If you look at this is the rotor hub. This is one offset, you can say hinge offset. From there you can have, this is the pitch bearing, okay, and pitch bearing is inclined with respect to the hub plane through an angle, that is pre-cone, okay, that is called pre-cone. If pitch bearing is inclined with respect to the hub plane. Now the blade can be inclined with respect to the pitch bearing, then that is called pre-droop. Okay. So pre-cone, pre-droop, these are two terminologies. Why this difference is, you change the pitch angle by rotating the blade about this axis. When you rotate about this axis, if droop is 0, the pitch angle will change like this. But if the droop is there, if I rotate about this axis, the blade will go like this. Okay. Not only the pitch will change, it will also move back and forth. You understand, because the axis of rotation is not along the blade, it is at some other direction. So this will go like this. These effects are very critical. Actually the pre-droop is called the pre-flap, that is the HL terminology. No, pre-cone I said. No, HL, because this is used by Germans, okay. But the Western means, I meant in US they call it droop and then cone, okay. ALH blade has pre-droop, okay, because the pitch is at that, blade is like this. So if you rotate, the blade will go like this, and okay. This is a geometrical, these are all, if you see what is the order is about 2 degrees. You know what is the effect of pre-cone, you say relieve the root movement, but it has aeroelastic coupling, tremendous influence. in terms of damp. Then already coning means I have shown here what is the difference between these two. It is, see, I am not sure whether one blade has both, okay. I am not sure. There are blades with only pre-droop, that is a ALH blade. There are blades only with pre-cone, okay. But there is a difference, geometrically they are different, they are not same, because they will introduce different effects in the aeroelastic analysis. But you can design a blade with both, this and
the blade, sorry.
here.
So there will be a hinge in it. What is
Hinge.
what is hinge?
No, earlier they had actually bearings, now they have elastomer, which is actually soft. Suppose if you want to see our blade has a, they have the what do you call, there is a centrifugal what is the thrust barrier. Thrust bearing is you hold this, okay, I am pulling it. If I hold it here, I am pulling it. Centrifugal force will pull the blade, I have to somehow hold it, but then when I pull the blade, it should not come out. So, I have to put a stopper, but at the same time I should be able to rotate, right. So, the kind of bearing is called the thrust bearing. It can take the axial load, but at the same time you can rotate it freely. So, it is like if you want to see, we have removed our thing, you will be able to, we removed, we assembled it. If you want, we can again easily remove the blade and then show it to you how it is assembled. You can have, very simplistically, you can have a okay. I have shown this is one plate, this is another plate, in between there is a plate with lot of ball bearing and there is a groove in this, it will come and sit in the groove, okay. Okay. You close it and the blade will be tightened from this side, you can rotate freely. This is attached to one, this is attached to the blade. So, you can easily change the pitch angle of the blade without any difficulty. Centrifugal, you do not have to overcome the centrifugal force. Okay.
But say if I am giving a pitch, so how will it, I mean, rotate? It will rotate in both ways, right? It will have a pitch and also
If it is a
this thing.
pre-droop, yeah, it will go like this, it will go like this. But it is all, you give only 5 degrees, 4 degrees, that is all, not much, 10 degrees at the most. The blade will go like this, obviously.
So then at the junction between the blade and the this thing shaft, I mean shaft.
See, what will happen is here, suppose I say the blade, it comes here and then it takes the shape. That means this portion is where I am attaching, okay. Now this is where the blade is, blade means this is the aerodynamic everything. This section is a part of the blade, blade can be manufactured like this. You can manufacture a blade like this, okay. I can have a bearing. Composite blades, that is why composite blades are easy to manufacture with that shape. Pre-droop, this is the droop, because you see metallic blade is tough, but composite blades are easy. The ALH blade is a composite blade, so it is there, okay. Advantage, that's I can only say in word. It, see, one is whether it is a pre-cone or a pre-droop. In the equilibrium level, equilibrium is whatever we obtained as the loads, it reduces the root load, that is equilibrium, root moment basically. But if you take effect of that on stability, stability means not blade stability, flap, lag, torsion. In that problem, pre-droop gives some damping, but it will increase the vibratory load, okay, in lead lag. But pre-cone will not give the damping, but it will reduce the load. So, you have to see the trade off, what you want, okay, whether you want higher load, vibratory load, not mean load, and this will have lot of effect in torsion. So, you see flap, if you look at it, both configurations there will not be major change, lead lag there will be a change, torsion there will be lot more change, which will go to pitch link load. Then you say which one is better. Okay. This debate goes on because changing a configuration from one to the other is not an easy task in the actual design. Finally, you live with it, whatever load that comes, and you try to minimize something here and there. So, but each has its own plus and minus.
And in case of a pre-cone, is it the flap hinge which is going to take the load of the blade? Because
No, pre-cone means pre-cone or
pre-cone.
yeah. See, it is the root will always get the root shear force bending moment. Okay. You remember I derived that ideal pre-cone. That means what is the root bending moment?
Suppose if it was a metallic blade.
Yeah, it does not matter. See, what will happen is aerodynamic load tries to take it up, centrifugal load tries to bring it down, okay, and there is an equilibrium. Suppose if your rotor blade is already kept equilibrium angle, there is no root stress. You follow what I am saying? That is why that is given, that pre-cone, relieving root moment in the blade. Otherwise, you have to make the root section a little thicker.
But it will also transfer as a moment to the flap hinge.
It will come, no, but elastic deformation. See, okay, you are always thinking this is another problem. Problem is not, we always think if you draw the bending moment shear diagram, please understand, cantilever beam, we always say root has maximum, you say bending moment. It is not so here, that is what you have to know, because if you take this beam, your lift force is here, okay, and CF is here. Actually, the maximum bending moment is not at the root. Okay, you can have zero bending moment. That is why you can have a hinge and you still have an equilibrium. You understand? So, you got it.
But my doubt was like
What?
the, where the pitch bearing is, where we are giving a pre-cone angle,
Yeah.
that point, that's a hinge, right?
Here.
Yeah.
No, there is no hinge.
Flap hinges?
There is no hinge in these things.
Okay.
This is the hingeless blade configuration I have shown. Oh, if you have a specific hinge,
Flap hinge.
that we will come to that. That is where I said, this is just a configuration, I have not shown actual geometry. Okay, this is a hingeless blade, I can design like this. I am just showing a schematic. If you take an actual blade, you can have the hinge at the near the hub, pitch can be outside, no problem. Or pitch can be inside, hinge can be outside.
So hinges inside, flap hinges inside.
Yes.
Then
When it flaps,
flash plate is going to get
yes, hinge, yeah, it will do. I will show you that geometrical thing, how it happens. That is why this was always a question, where do you put the hinge? But most of the hingeless blades, actually pretty much, because I know ALH blade, the pitch bearing is inboard, okay, and there is no flap hinge per se, but there is a equivalent flap hinge, some soft stiffness drops at some section where that becomes kind of a hinge. it is a virtual hinge. It is not a physical hinge, but some point is soft, therefore, it can flex about that point. Okay. But the pitch bearing is inboard. Most of the hingeless blade pitch bearing is inboard, you do not keep it outside. Okay. Most of them, but you see that goes into construction. Now, the next from top if you view, of course, this is just to I have said that pre sweep. You see the axis of the blade need not pass through the center of the hub. It is not that the blade is attached here, it can be attached, but it can also be offset by some small distance. This is called torque offset. Okay. Torque offset, this is. If you really see what is that distance, that will be about 10 mm. Okay. It is all, it is not a lot. Usually it is a very small distance. And of course, I have exaggerated this because saying that suppose if you have a tip, the blade can be straight and tip element can come here. Only tip, one small section of the blade can be swept back, that is a tip shape. So, the entire blade is swept, but of course, no blade is made like this. Now, this is the torque offset, these are hinge offset and pre-cone, pre-flap or pre-droop and then pre-sweep. These are the geometrical complexities in a rotor hub, but it is not necessary that all the rotor blades should have everything. That depends on the experience of the manufacturer. Okay. How do we analyze this problem? I will just show idealization of a elastic blade as spring restrained rigid blade model. This is you are idealizing. This is the elastic blade. I have shown here just for example. If you have a small element, because this is how we analyze structures, you take a small element of the blade, how this small element deforms during operation. This element can have an axial deformation U, a lead lag deformation V, a flap deformation W, and then it can have 3 rotations. Okay. Now, this is the model of a elastic blade. Now, if you want to really follow systematically, because based on that it is a basically displacement formulation we do. You assume a displacement and then get the strain, then once you get the strain then go to stress and then write your equilibrium equation. From there the standard technique starts, but of course you have to take the centrifugal load into account. This modeling was started only in the I would say 50s first paper, then of course 80s people were really 70s to 80s lot of groups were, lot means about 3-4 groups, that is all, not many. But simultaneously they were trying to get a simple model which is a rigid blade, but represent the entire elastic properties by a root spring restrained rigid blade. So, I have 3 springs I have put. This is the torsional spring, this is the lead lag spring, this is the flap spring. This is an arrangement. Okay. This is my own idealization. Okay. Now, I idealize my rotor blade like this, and then I go ahead and solve all the problems of rotor blade by this model. I will not bother about this, but only thing is the question will be what should be my spring constant. Okay. You try to match the fundamental natural frequency of the blade, only fundamental first mode, because elastic blade it will have infinite natural frequencies, first mode, second mode, third mode, fourth mode, etc. If you study vibration, then you will know. So, otherwise you know spring mass system, you have one spring mass, single degree of freedom, one natural frequency. If you have a 2 degrees of freedom, you have 2 natural frequencies, 3 degrees of freedom, 3, infinite degrees of freedom, infinite natural frequencies. Okay. Rotor blade has infinite because it is a continuous beam, but for practical analysis usually they take about, that is from design point of view. Flap you take about 3 or 4, lead lag 2 or 3, torsion 1 or 2, flap mode 3, you take 3 or 4, but usually 3 flap, 2 lag, 1 torsion. Some people may say, okay, I will take 4 flap, 3 lag, 2 torsion and 1 axial. We take 1 axial mode because that has to bring in some effect. Okay. But you look at the frequencies. So, in the rotor blade, in the dynamics group in the helicopter, they analyze some, of course, couple of guys, their job is to run every day what is the natural frequency, mode shape, natural frequency, mode shape in each mode. Okay. We have developed a code now that is given to HAL. We can analyze for a actual blade. Of course, there are lot of small details which we have to take into account, a real blade. Once you have the code ready, every day you will run. You may not know how it is developed, okay, but that is a finite element code. But this is a idealized model. Most of the rotor analysis packages in the earlier days, they used only this model because it is easy, you can understand the physics, but it is a gross idealization of this. You are representing only one flap frequency because there is a flap spring, then there is a lead lag spring, one torsion. So, you will have 3 frequencies, that is all, and the blade is rigid straight blade, that is it, it is a rigid blade. Okay. So, you can get certain phenomena correctly, reasonably good, but you can't get the vibration and other things because this is not a true representation of this. So, you will not get all the other loads, it will be in error, but you live with it. Okay. Today, of course, people want to have elastic blade model. Of course, there are several research groups who have developed it and they are also working on further developing the code. Okay. Now, we take first the flap, because we have been studying flap, I will briefly describe the flap model. First, isolated flap. Isolated means only flap motion I am considering. I am not considering lead lag, torsion combined, because the moment I combine, I can show the equations. Okay. Now, you see, I have slowly I am complicating my blade model. Earlier we had a centrally hinged and we put a spring restraint. Now, I am having a offset and a spring. Okay. This is what a real life blade is. You can represent it equivalently offset hinged spring restraint blade model. Okay. Even our blade is also similar. Now, you have to write the flap dynamic equations for this model. Of course, the procedure is identical. You take any, I have given a pre-cone, this is the undeformed axis, from there the blade deforms. So, take any point, find out its velocity, find out its acceleration, then take the inertia force, then balance the root moment about this point. because here is the root spring. Okay. You balance the root moment, take the aerodynamic load, and you will have, but now the length of the blade is different from the radius of the disc, because the radius of the disc is E plus the length of the blade. Okay. So, you have to be R minus E. R is the rotor radius, E is the hinge offset, and this is non-dimensionalized with respect to rotor radius, I call it L bar. Similarly, E bar is the non-dimensional hinge offset. Okay. Now, I have to have this, and then I derive my equation. Equation I am showing it here, I am not deriving, you can have a look at it in the notes which I send it to you, but we will discuss this part a little bit in detail. Because of just the hinge offset, nothing else, I have not done anything more between the earlier development to current development. Only thing is I added a hinge offset. Hinge offset will add lot of additional terms. Okay. When you put that E bar 0 and L bar as 1, you will get back the old equation, what I had sent it for you. Okay. Otherwise, everything is same. Now, you see every small geometrical parameter you add, your equations becomes a little bit more lengthier, and that is why otherwise one can really develop the full equation, then start reducing it, but that is only when you understand fully you can go, otherwise you start from basics, then slowly proceed further. And I gave you as a assignment which you all have solved only this problem, flap equation with E bar 0, L bar as 1, and I knocked out all the except the there is a dot here. Okay. Knocked out all the right hand side, you solved, given an initial condition how the response looks, that is what the problem you solved. Okay. I would like to discuss this particular thing a little bit carefully because of the introduction of the hinge offset. What happens to the natural frequency of the blade in flap mode, rotating natural frequency. Okay. If I take the hover case, very simple, I can reduce this for hover. Hover means just put mu 0, it will become the hover. So, let us take the hover case. Okay. We will and I have done one more approximation there. Okay. That approximation I will mention to you, so that I can write the equation here. All the derivatives are with respect to non-dimensional time. Beta double dot, this is gamma Lock number. I am just writing it for mu sin psi beta dot. Then you add beta term, maybe I will put it here, plus beta into 1 plus, I am writing here slightly differently. Please note, later I will show you what this particular term is. This is the root spring I b omega square, this is one term, plus gamma over 2 mu cosine psi L bar cube by 3 E bar 2 plus mu sin psi L bar square over 2, sorry, this bracket I close it, this I close it, this I close it. Okay. This is my stiffness term, please understand. I have 1 plus this, I will explain to you what this term is, root spring divided by blade mass moment of inertia non-dimensional omega square. This is due to the aerodynamics gamma, and this is a time varying. This is only with respect to mu, forward speed. If forward speed is 0, this term is 0. Okay. And then the right hand side you will have equals gamma over 2, you will have the control input 2 E bar L bar cube over 3 E bar square, anyway this mu sin psi 2 E bar, okay, plus mu square sin square psi L bar square over 2. This is into theta control input, that is theta pitch input, what the pilot gives, theta naught plus theta 1 c cosine psi plus theta 1 s sin psi, that is this term. And then I will have minus inflow term lambda L bar cube over 3 E bar L bar square over 2 plus mu sin psi L bar square over 2, and then I will have precone terms beta p 1 plus m x c g E over I b plus mu cosine psi L bar cube over 3 E bar L bar square over 2 mu sin psi L bar square over 2. Okay. This is my entire equation. Now, I will tell you what those I b as a definition, okay, because that you have to know what is MXCG, what is IB, etc. Because IB integral 0 to r minus E m, okay, x starts from the hinge offset from here, basically moment of inertia. Then m is mass per unit length. Okay. And then mass of the blade mb is m dx. Okay. Why I am taking, see there I assume that the mass is uniform, okay, whereas rotor blade need not have uniform mass. Of course, the major aerodynamic section is uniform, but the blade mass can vary little bit along the span. If you take this term, if it is the uniform mass, this will become, if m is constant, this will be m r minus e whole cube over 3, r minus e cube over 3. This will become m r minus e square over 2, okay, if m is constant. Now, if I substitute in this place, that will be m x c g e over I b becomes your m r minus e whole square e over 2 divided by m r minus e whole cube over 3. So, this will become 3 e over 2 r minus e, which you can write it as non-dimensional. If you divide by r everywhere, this will be 3 over 2 e bar over L bar, where L bar is r minus e over r. Okay. If m is constant, and that is what I have written here, 3 over 2 e bar by L bar. Okay. This place. I have assumed that the blade is uniform. All right. Now, let us take this equation. What is the frequency? Because this is a non-dimensional thing. If I reduce to hover case, automatically what happens? You know that this is x double dot plus some x dot plus some x equals some right hand side equations. Only thing is the coefficients are of course time varying coefficients, which you have seen. We do not have any closed form solution for this. Okay. This is the equation, this is the equation. Now, you can analyze steady state response. That means, if I prescribe my input, find out the steady state value, what is the response of the flap motion. You know that immediately you have, because theta, this one, you have theta naught 1c cosine psi plus 1s sin psi. Okay. You have already second harmonic, this gets multiplied, third harmonic, you will have all the harmonics can come. So, when you do, you neglect everything, I take only first harmonic, but that is not correct, because as you go to high speed, you will find slowly second harmonic will dominate than the first harmonic. But this is the assumption we make, we neglect and our results will be wrong, but it is okay, you take it, all right, something I am getting some trend. This is what, otherwise you have to take the full thing. Okay. So, for the preliminary study, there are two things you can analyze. One is stability of the system. That is, you take the right hand side, you put some initial condition, you have analyzed that problem, which I gave it as a assignment problem to you. But that was simplified, please understand, because you did not have this term, you did not have this term, you had only 1 plus, and these are all 1 by 3, 1 by 2, you had only this. Okay. If you look back your equations, here I am having a little bit more complicated. So, this particular term 1 plus m x c g e over I b plus k beta over I b omega square, this is my rotating flap natural frequency in hover, because this is not there. The moment I set mu 0, my rotating flap frequency, which is omega bar r f square is 1 plus mxcg E over IB plus K. Okay. This is my rotating flap frequency, and if my mass of the blade is uniform, then I will have the same expression simplified as 1 plus 3 by 2 E bar over L bar plus, okay, if m is constant. Now, you see, even if I do not have the spring, okay, if I have an offset, root offset, that is root hinge offset, my frequency is more than 1. That is, my flap frequency will be more than 1 for a rotor blade always. But if I put a spring, I add one more stiffness term. So, you just see the root hinge offset gives a stiffness basically. Your flap frequency is more than 1. Now, how much? So, this is where the hingeless blade, articulated blade, that key difference. Articulated blade, you do not have any spring, that is gone. So, you usually have in the range of articulated rotor, it is around 1.0, I think 2 to 1.04, whereas hingeless you go to 0.9, 1.1 sometimes, because physically you need to have some, because you can't put the blade right at the center, there is a physical dimension. So, articulated blades have flap natural frequency is in this range, whereas hingeless blades slightly higher. Now, if you want to find the equivalent hinge offset, okay, without the spring, hingeless blade you do not know, there may be, you can always say this is having a hinge offset which is larger than articulated rotor. More hinge offset because you have a more flap frequency. More flap frequency, you remember earlier I said hub moments, you will have a higher hub moment, omega bar Rf square minus 1 over gamma by 8, remember. That means, if you have a higher flap frequency, you will get a higher hub moments. That means, pilot will have, he can generate more. Now, this is where how much higher you can go, can you go further, then they will say it becomes too sensitive. So, they try to keep it only maximum in this range, do not go too high, otherwise higher flap frequency, your higher moment, higher vibration. So, you will find the problems will be, if it is hingeless, your vibratory loads also are higher. So, you get a control moment high, but your vibration is also high. Now, what is the choice? So, this is where every parameter, everything, there is a plus point, there is a minus point. Plus
Does the control moment affected by the
flap frequency. You remember Cmx, Cmy, that expression was what? Omega bar Rf square minus 1 divided by gamma by 8. Omega bar Rf square, if it is higher, you get a higher moment, right? Higher control moment you get. Higher control moment means pilot for a unit stick motion, he gets a large moment, he generates more moment. Okay. So, that is why the flap frequency is very, very important in actual helicopter design, but you can't have anything you feel like. because finally the pilot's opinion matters. If you feel it is too sensitive, then you have to go back and then redo the entire design. Okay. But this is the range. Now onwards the course will be like this. Few, I will deviate. Huh? Yeah. Yes. Control response, I don't know, I cannot immediately say. It's a very tricky question you are asking me. Usually, I don't think that is analyzed from that point of view, pre-cone and pre-droop, because I will tell you, just flap equation alone if you take, only flap equation, there is no difference between these two, except for the root loads. Okay. Whereas, if you look at the damping, damping means I am talking about aeroelastic damping, not the vehicle damping. Aeroelastic damping of flap lag stability, then lag damping will be influenced by whether it is a pre-cone or a pre-droop. Pre-droop actually improves the damping. Okay. And if you look at the loads, pitch link load will be higher in case of pre-droop because of the torsional coupling. Torsional coupling, it will be there, you will get a higher vibratory load. Now, from the point of view of vehicle stability, I won't make any statement now because I don't know. It's unless we solve the problem, we will not know, because if I make assumptions that it's only flap motion, then I may not be able to see any difference. And most of the vehicle dynamics is analyzed only with flap, because they do not take lead lag, because the flap motion controls vehicle dynamics to a large extent. Okay. That is why if you see the flight dynamic equations, they will take flap. But later somebody said that damping is not properly predicted in the vehicle, so it will take lead lag, but then problem becomes messier, your understanding also goes down. Maybe when we solve the full problem, hopefully we will be able to answer your question, but today I do not know. Okay. But if you consider only flap equation, you will not see any difference, you will not see any difference, you will see both are same. But if you consider flap and lag, then you will start seeing the difference between pre-cone and pre-droop. You will see in the stability, you will see the difference in the results. Okay. All right. Now, this much for the frequency. So, I have given here essentially what I have written there, I have reduced it to the hover case, of course, with the offset E, etc. So, this is just for comparison. The frequency, I said, because you know that spring mass damper system, you will have x double dot C over m x dot k over m x, and this term is C over m is 2 zeta omega n. Zeta is the damping ratio, and this is omega n square. So, this is the natural frequency. Natural frequency is this, that is the rotating flap natural frequency. Now, you know what hinge offset affects. Hinge offset influences the flap natural frequency. Actually, it increases the flap natural frequency. Okay. Now, what is the value of the damping ratio? You can take a crude approximation here, and then you have to, because this term 2 zeta omega n is essentially this term gamma over 2 L bar over 4 by 4 E L bar, E bar actually E bar L bar cube by 3, that is the damping term. Now, if you look at you all have studied the single degree of freedom system, and what is the eigenvalues, and then the the roots of the equation you will write e power minus S t, and you will write S as minus zeta omega n plus maybe I omega n root of 1 minus zeta square. You are familiar with this, because this is the equation. Omega n square x is 0. This is the homogeneous part equation root, okay, because you say that zeta is actually less than 1. So, you analyze the roots, you will get the 2 roots s 1 comma 2, then you will substitute e power this, you will get a decay and a sinusoidal. This is a simple single degree of freedom damped system solution. So, the damping here, if I substitute, that is zeta omega n. So, e to the power minus zeta omega n t, this is how my amplitude will decay. This is the decay term. You correspondingly take it to this side, you will see e to the power minus zeta omega n is our natural frequency, of course, omega n, but of course, since we are dealing with the non-dimensional everything, this is also non-dimensional, I will put a term tau, okay, zeta omega n tau. Usually what they do is how much time it takes to decay to half the amplitude, that is what people take. The time that is the time constant, okay. The time constant usually they say how much time it takes to decay to half its amplitude, means what is the time it takes from 1, initially 0, it will be 1, how much time it will take to get it 0.5, okay. That is the decay, and that value is I think 0.693 or something like that, okay. I will just briefly mention here, okay. That is this tau for half. You take this value as approximately 1, do not try to take it, because you know that this is 1.09 or 0, you take it approximately as 1, then you take this. So, the time for this is half, sorry, not tau, time for half amplitude will be 0.693 divided by the real part, negative real part of this is zeta omega n, okay. Omega n we took it as 1. So, zeta, what is our zeta omega n from here? Gamma by, because you look at our equation, 2 zeta omega n is gamma over 8, okay, approximately. That means this is taken as 1. So, zeta is gamma over 16, okay. So, here it will be zeta, this is 0.693, that is gamma over 16, you take 16 here, you take gamma here, okay. If you take gamma as 8, gamma equals 8, the value becomes non-dimensional time, okay. The time for half amplitude becomes 1.386, this is non-dimensional time, okay. Now, if you want dimensional time, tau is omega t, okay. So, you will get t is 1.386 over omega, if you take omega as 32 radians per second, because which is reasonably good number. If omega is 32, you will find, I am just writing it, why I put all these numbers is just to give you an idea, 0.0433 second, 0.043 seconds. For this omega, that is 32 radians per second, the time it takes for one revolution, time for one revolution, okay, is 0.1963 second. Okay. So, for the blade to go around once, it is around 0.2 seconds, okay, whereas the amplitude decay, it happens in 0.04, which means the time constant is really very small, in the sense it quickly reaches its value. That is why when the pilot gives any input, the response of the flap is quick. He won't recognize or feel a delay in the response of the blade. You can take it as though input output is instantaneous, even though there is a slight delay, but that delay you neglect. Why this is important is, this particular number what I used to indicate, I can now make approximation, which is called the quasi static approximation. I really do not bother about, now I am coming to our flight dynamics. Flight dynamics, because pilot gives an input to the rotor blade, blade immediately flaps, then it gives the hub moments and the helicopter response. The delay between pilot input to the response of the blade, I am neglecting it. I say that it responds instantaneously. That means the flap dynamics I neglect, I look at the steady state value. I give this input, I neglect the dynamics, only steady state. The moment I look at the steady state value, the dynamics is gone. Give input, there is a change in force, that is all. How the change in force has happened is because of dynamics of flap motion, the change is happening over a time, but I neglect that. Okay. So, when I solve flight dynamics, they really neglect even the flap dynamics, in the sense they assume it is quasi static, not that flap dynamic equation is thrown off, but I say I give an input, instantaneously I change my loads. That is because of this. In one revolution it takes about 0.2 seconds, whereas the flap decay, that is response, time constant, it comes to that small value 0.04, which is about 20% of this. It means very quickly it responds. Okay. This is the beauty of the flap, and this number is the one which makes further analysis. They will say, okay, I can make it simpler, and you start analyzing flight dynamics based on this. Okay. Now, you see, when you really solve flight dynamic equation, you will not have flap dynamics in your model, you will only have fuselage equations. And where is the blade dynamics gone? It is taken as change in force, instantaneous change in force. Okay. That is because of this quickness. Okay.